Unicorn Zombie Apocalypse.
Hello everyone, welcome back to Eco Talks with Sneha Manarikar. In today's session, we'll discuss few more questions from linear programming. So let us start our session with first question. Any column or row of a simplex table is called A vector, B key column, C key row, D none of the above. Answer is any column of or row of simplex table is called as a vector. Here is the example of the simplex table. Here we have CJ. CJ are the coefficient value, LHS of the constraints. And whereas here CB column is the coefficient of the basic variables in the objective functions. And these are the coefficients of all the basic and non-basic variable in the constraint equation. Now, this here Zj minus Cj we will be calculating to get the initial basic solution. So this is the standard format of simplex table. So each column or row here is called as vector, whereas the whenever we find the key element by intersection of outgoing row, outgoing factor and incoming factor, that is called as key element, and the key element is present in which column, it is called as key column, and row it is called as key row. Otherwise other all are called as vector. Next question is, if there are m original variables and n introduced variable, then there will be dash columns in the simplex table. A m plus n, B m minus n, C 3 plus m plus n, D m plus n minus 1. So there are m original variables and n are introduced, that is our artificial variable, it will be slack or surplus variable. Then number of columns will be 3 plus m plus n. This is because 3 columns will be fixed in the simplex table, that is CB, basic variables, and XB. Then next whatever the columns will be, that will be our this variables in main objective function plus the later added variable. So you can see here in given problem objective function there are 2 variables x1 and x2, but later to remove the inequalities we have added 3 surplus variable or slack variables, the S3, S4, S5. So number of columns will be 2 plus 3 plus again these 3, which are the fixed columns in the simplex table. So total number of columns will be 3 plus 2 plus 3. Next question is, minimization problem can be converted into maximization problem by changing the sign of coefficients in A constraint, B objective function, C both A and B, D none of the above. Suppose if minimization problem is given and we have to convert it into the maximization problem. So we can do it by changing the sign of coefficients in objective function, because maximize and minimize where it is given in the objective function. So we have to change sign in objective function. Here, see here example is maximize 3w plus 2p. So we have to convert maximization problem into minimization. Just change the sign. Or even if you want to convert minimization problem into maximization problem, just change the sign. By changing the sign, you can convert maximization into minimization and minimization into maximization. Next question is, if in a LPP a solution of a variable can be made infinitely large without violating the constraint, the solution is, LPP means linear programming problem. The solution is made infinitely large without violating the constraint in the solution. It is A infeasible, B unbounded, C alternative, D none of the above. Answer is, it is unbounded, because the solution is made infinitely large. That means it is not bounded to a particular region. That is, it is unbounded. So this unbounded solution, when determine the leaving variable of any table, that is of any simplex table, when we determine the outgoing variable, if there is no positive minimum ratio, all entries of pivot column is this minimum ratio column, are negative or 0, then this unbounded solution situation occurs. Now you can see here in the problem, Now when we consider now minus 2 is there. Here this is the incoming variable. Now x1 will be the incoming variable. To calculate the outgoing variable, we have to see the minimum ratio. That is positive minimum ratio. So here now all the variables are here in negative. So our minimum ratio also will be in the negative. So in such situations, there will be unbounded solution. That is no perfect solution. It can be any values can be taken for the as a solution. So this is the unbounded solution. In graphs, we can see here when now is you can see a problem. It is given minimize z is equal to 40x1 plus 60x2. But all the substeps to constants are greater than sign. So that means the region at the right hand side of the line will be a solution. So when we see the common area here, the area beyond the line, this line RQP PQR, this line, this shaded line, there will be a solution. So any points with farther the point you take, that much the larger your solution will be. So that it is the unbounded solution. That is your objective function will be made infinitely large. You cannot say that this is the point where we get the maximum value of minimum value of z. It goes on increasing as we move on further. Next question is, in maximization case, that are assigned to artificial variable as their coefficients in objective function a plus m, b minus m, c 0, d none of the above. Answer is, in case of maximization problem, when we add artificial variables, we assign minus m coefficient, whereas in case of minimization problem, when we add the slack variables, our coefficient will be 0, but for artificial variables it will be minus m. You can see here, we introduce a non-negative variable to the left-hand side of constant greater than or equal to type. These variables are called the artificial variables. The purpose of introducing artificial variable is just to obtain an initial basic feasible solution. However, addition of this artificial variable causes violation of corresponding constant. Therefore, we would like to get rid of these variables and would not allow them to appear in the optimum simplex table. To achieve this, we assign the very large penalty, that is minus m, to these variables in the objective function for maximization objective function. So when to find, in order that these artificial variables will not appear in our optimum solution, we assign them the large penalty. Large penalty is minus m for as a coefficient in the objective function. Next question is, in simplex method, we add dash variable in case of equal. A slack variable, B surplus variable, C artificial variable, D none of the above. Answer is, when we convert it into equal to situation, we add the artificial variables. So in artificial variable technique, this is also simplex method, also called as big M method, because we assign the big penalty in case of artificial variables. So the modified LPP as follows: minimize z is equal to 2x1 plus 2x2, 0s1 plus 0s2 plus ma. Now here it is the minimization problem, so we have given the plus sign, whereas in maximization, if it was, we would have given it minus m. ma1 plus ma2. Subject to constant will be 3x1 x2 minus x1 plus a1 is equal to 9. Now, x1 plus x2 minus s2 plus a2 is equal to 6. Okay. Now this will be the unmodified objective function in case of maximization. See, when we turn the minimization problem, we change the sign. This minus 2x1 minus 2x2. For here, as it is 0 coefficient, plus or minus won't affect. So we keep it as it is 0 x1 plus 0 x2 minus ma1 minus ma2. Next question is, if there are more than one optimum solution for decision variable, the solution is A infeasible, B unbounded, C alternative, D none of the above. The answer is, when there is more than one optimum solution, then the decision variable is called to be alternative. Here, first let us understand the simplex method. What we'll do in simplex method, after plotting the simplex table, just will determine the basic feasible solution. By determining that, we'll determine the entering basic variable by selecting the non-basic variable with most negative value or with most positive in case of minimization. And if there is no this condition is not fulfilled, then it means we have attained the last solution. Otherwise, we'll go to step 3. That is, we find out the living variable, that is outgoing variable, and then we determine the new basic solution. This is the in short about the simplex method. Now here you can see the format of simplex table. So here x1, x2, these are the non-basic variables. These are the variables which are present in objective function. S1, S2, S3, these are the basic variables which we have added in the objective function to make the constraints which were in equality to we have converted into equality by adding this S1, S2, S3. Then this is the minimum ratio. This is the Z row. Here C1, C2, it is the coefficient of objective functions, or that decides the entering variable, and based on minimum ratio we decide the living variable. So this is the simplex table. Now alternative optima, what it is, if Z row value for one or more non-basic variable is 0, then optimum table alternate optimal solution exists. Now here, if this is the Z row for any of the non-basic variables. Now here, if the value comes 0, then the problem of alternate solution arises. So that is, we can take this either, suppose if for x2 it comes 0, Z row comes 0, then we can consider this x2 as the as the basic variable, because it does not affect its coefficient is 0 and it does not affect the our objective function. So we can convert it in basic variables without altering our objective function. So this is called as alternative optima or alternative solution. Next question is, who developed linear programming for the purpose of scheduling the complicated procurement activities of United States Air Force? A. George B. Danzig, B. James B. Danzig, C. George B. Dante, D. George B. Danzig. Answer is, linear programming was developed by George B. Danzig. He has developed the concept of linear programming. Next question is, who originally called it programming of interdependent activities in a linear structure, but later shortened it to linear programming? And option A, Danzig, B, Cantori, C, Marshall, D, none of the above. Answer is, the term linear programming was coined by Danzig because he has introduced the concept of linear programming. He has coined the term linear programming. Next question is, LP can be applied in farm management problem. It relates to the allocation of resources such as dash in such a way that it maximizes net revenue. A, acreage, B, labor, C, water supply or working capital, D, all of the above. Now, linear programming can be applied in farm management in allocation of scarce resources. In which are those scarce resources such that we make our maximum revenue? Answer is all of the above, because it can be applied for acreage, that is which crop should be cultivated for how much area. Labor, allocation of labor for different enterprise or different crops. Then water supply and working capital, how much water supply should be provided, in what pattern it should be provided. All can be calculated by using linear programming. These are the applications of linear programming. Now, important applications of linear programming. First, in military application, it has originated from military operations only. So first one, it is selecting an air weapon system against the enemy. Which weapon should be selected, in how can it be economically efficient, and also the damage will be more. These all questions can be solved by linear programming. In agriculture, in farm economics and farm management, in allocating the scarce resources. In environmental protection, handling waste and hazardous material. Facilities location non-public health facilities. Next, product mix, the existence of various products that company can produce and sell, that can be also obtained by linear programming. So likewise, these all are the important applications of linear programming. Linear programming also helps in to solve the transportation problem and allocation of labors. These all things are the applications of linear programming. That's all for today's session. If you have any doubts, you can ask me in the comment section. And don't forget to like, share and subscribe to my channel EcoTalks. Thank you.